Welcome everyone to join this session about frontiers of agentic AI. Yeah, so it's my great pleasure to be here because actually when I built the AutoGen, there were a lot of open source community members who are actually from this area. Yeah, I don't know how many of you are like from local, like in Croatia, and all the rest of you from Europe, other places of Europe. Okay, good. And are you? So I don't know the background of the audience. Are you like graduate students? Could you raise your hand? Undergraduate, or professors? Okay, so then what are the rest of the people? Are you, if you're not graduate or undergraduate student, are you like developers? We're working industry. Okay. How about researchers? Like, who are you like doing research? Okay, quite a few. Okay, got it. Thank you very much. Yeah, so let's have some fun for next. So I guess I start at 9:20. Is that right? Okay, cool. Got it. 9:10. Until 10. Okay, 9:10. 10:15. Okay, got it. Cool. Yeah. Is there a microphone for the audience to ask questions? Okay, cool. Yeah. I can do it during the session. Yeah. So feel free to kind of raise your hand, ask questions anytime you want. I want to make this interactive session. Yeah, so I'm going to talk about agentic AI. So this is like the top area I've been working on since the last maybe 2 or 3 years. When I started building like AutoGen or AG2, I dreamed of an AI system that can learn alongside with you and grow with you during the interaction. Solve very big, anytime, any hard problem for you, and also necessarily when it's necessary, collaborate with other agents. Yeah, so that's kind of the dream kind of AI system I'm dreaming about when I start building that and lay the foundation. And over the past 2 years, I think the industry has made huge progress. So I want to kind of share with you about this journey, both about this AutoGen and AG2 project since its beginning, and also talk about what's the new progress the industry has made, where are we in this aging AI space, and what remains to be challenging problems that's good for further research. Yeah, so that's kind of the overview of this session. I just don't know, like, how many of you have ever built an AI agent? Could you raise your hand? Nice. Yeah. What have you built AI agents for? An example? Yeah.
Brief your meetings. You can ask like lifetime questions with your meetings. I'm connecting LLMs with rack systems and like calendars, other tools.
Yeah. Okay. Manage your daily work. Yeah. Productivity. Very nice. Any other one want to share?
I built one that will recommend financial news that should tell me whether I should invest in a stock or not, and deploy it in a WhatsApp bot.
Nice. Trading agent help you do investment and trading. Nice. We also want to share? Cool. Yeah. So sounds like we have some people who have built agents before, has experience before, and who has never kind of built an agent, AI agent. Okay. Yeah. We also have beginners, and for people who are building AI agents, have you used any framework, open source framework like AutoGen or any other open source framework? Could you share? Or do you just building agents from scratch? you want to say something? Yeah. Copilot. Yeah, nice. Nice. Anyone else? So Copilot is like a no-code interface, right? Okay, nice. Have you used any develop like a coding framework, or just building that from scratch? LangChain, nice. Yeah. Any other example? Yeah. DSPy, nice. Okay. That's the optimization framework. Yeah. Anyone else? Sorry. Atomic. Oh, I don't know that one. Yeah. So is it an open source framework? Okay, nice. Cool. Yeah, great. We have quite diverse experience. Yeah, I can share some of the lessons learned from building those open source frameworks. Yeah, so before that, I still want to kind of talk about the high level about this North Star of AI agents. So what is ideal or dream the AI agent that we dream for the future? So there are 3 dimensions. There are different layers. So they're covering the interface layer, so that the AI agent should have very natural way to interact with the human, so that you can you use your most natural, most comfortable way to deal with them, like talking with them or sharing information seamlessly. And then second dimension is a strong capability. We want agent to learn from the human along the way and improve themselves from interaction. And the third dimension is about architecture, so that we can scale up the power of them using the multi-agent architecture. I will explain them in more details. So that's just a high level with the North Star, and we're still not there yet. So we still don't have the agent that can satisfy all these dimensions to the best extent, but we're making progress all the way from beginning. So the progress has been very amazing since the last 2 or 3 years. When I started building AutoGen, for example, in 2023, there was no real generic agentic framework to build generic purpose AI agent for any application. But we realized that at that time, very early, that this is going to be the future. It's the future way of building software, and there will be a lot of needs for developers to reason about these complex future AI systems, and we want to enable them to build all sorts of applications. So that's why we built this open source agent OS, initially named AutoGen and recently named to AG2. The design considerations here are the main consideration is we want to simplify the developer's thought process, so that we can have a very intuitive agentic abstraction, and we want to enable them to do all the advanced exploration and satisfy all the diverse requirements. Like we heard from the audience that they're building all different kind of AI agents, and each of them will have some unique requirement that we want to enable them to achieve all of them. And also we want to provide minimal engineering complexity by offering reusable components. It's not easy to satisfy all these different requirements, but any good agent OS or agent framework should satisfy all these different requirements. And definitely different frameworks will have different like design principles. And here in AutoGen, the most essential principles can be explained easily with this single slide. We want developers to reason about any arbitrary complex application in simply 2 steps. The first step is to define agents of different roles, and the second step is to get them to talk. So as simple as that. The first part for this agent abstraction, AG2 has a very generic notion of AI agent. Here, the AI agent it's most kind of common sense, meaning that we want to be broad. I want to cover all the diverse understanding, because some people think the AI agent must be very, very clever and can do many different things. But other thing, people think as long as it can interact with a human and solve tasks piece by piece, step by step, they can be qualified AI agents. We want to cover all these different spectrums. And so here we can consider two types of agents. The first one is the most primitive agent that uses a single backend to generate replies. All these agents share the same interface. They can all receive messages, send messages, and generate replies. But the difference is what kind of capability are they using in the backend. So the most primitive agent just use one of the three types of backends. The first type is using language model. So that's the first most natural way in this language model era. And the second type of backend is to use non-language model tools. You can use any traditional code to generate those replies, or use other machine learning models that's not language models. And the third type of backend is human input. So the agent, for example, can simply take human input and send that to other agents. And in general, you can also mix these different type of backends to define a primitive agent. And you can customize their roles. Even when using the same backend, you can define, you can instruct the LLM to play different roles and perform different functionalities. So that sounds very primitive. So they can only do maybe very simple things. But how do we build more powerful AI agents? The answer in AutoGen is quite simple. You start with those simple agents, and you connect them to each other, make them collaborate or like coordinate in different conversation patterns. Just like how you manage a group of humans to make them perform more complex tasks by giving them instructions to collaborate. So here we use the notion of conversation programming, and there are a few predefined patterns, conversation patterns you can use directly to allow them to work with each other. The first pattern is called sequential chat. That means the agents follow predefined steps. Only when the previous conversation finish, the later conversation start. And the previous conversation will pass certain important information to the next step, so that they don't completely lose the context, but also don't need to know the full context of the previous conversation. So there's certain context selection process at the end of each conversation. And nested chat is similar, except that the chat can happen inside a single agent. For example, you can have an agent that manages many different subtasks like calendar or email and other different tasks. But there's a single agent as an interface that talks to the user. So user can ask many different type of questions, and the interface agent will manage many sub-agents and dispatch the tasks into different agents, or sometimes invoke a team of agents to solve the complex tasks. But all these inner conversation happens only inside that a single agent, and from outside, they don't know there's actually multiple conversations happening inside. So that's what we call nested chat. And this is a very powerful way, because as soon as you build a strong single agent, you can use this nested chat to build recursively more complex agent. And further, you can further combine with other agents so that you can build stronger and stronger AI agentic system without without necessarily letting users to worry about these complex interactions happening behind the scene. Group chat is another type of chat. It's also very intuitive to understand. For example, when currently, so this is a room with like more than maybe 100 people or maybe tens of people, and we all share the same context. So everyone can speak, and everyone can also hear the speech of others. So everyone just share information in the same room, and we can dynamically decide who to speak on the fly. And in general, you can also define some handoff patterns so that after one agent finishes, they can specify who to speak next and what to do for the next agent. And you can also define this conditionally depending on the current situations and the roles of each agent. And you can combine all these different conversation patterns and use them as building blocks to build any complex AI agent system. Or you can also customize your own patterns using this basic interface. And remember that each agent, all the agents share the same interface, so that you don't necessarily need to differentiate one AI agent versus one agent that represents a human being. So human and AI can also seamlessly participate at the same in the same temporal conversation using all these different patterns. Here's one concrete example of how you can orchestrate multiple agents to solve a real problem. Let's say we want to build a customer service agent, and this agent needs to handle all the different kind of requests from a customer. And in this case, we see that we can define several different agents. There's one customer agent that represents a human. This is what I meant earlier by using human input as a backend. So in this way, you can easily kind of add human participants into your system and model them as just one conversation participant. And there are a few other agents called authentication, order triage, and order management. So these agents all are all like language model-based agents, but each of them may have different set of tools and different system instructions. And you can see that there are different transition instructions from agent to agent. This is good for doing task separation, so that each agent focuses on relatively simple tasks. So even when the task is very complex, overall task complex, you can always decompose them into smaller problems, and so that each agent can finish the task more reliably. And the transition from agent to agent can be defined based on language instructions. For example, whether the task requires we triage the order or requires us to use order management agent to handle it. In other cases, you can also use programming language to define the rules and using so that there's no ambiguity. You can mix these different types of instructions. We also see that there are some different contexts shared among the agent. This is a group chat example. So all the agents not only have access to the conversation history, but also have access to some shared variables like the user database or the workflow context. This allows agents to collaborate in the common context so that they understand whether the order has been handled or not. They understand what's their responsibility. And these dynamic contexts will also be used doing the handoffs. So we are not simply relying on the natural language model's capability. And on the right-hand side, you see that the order management agent is connected to two other agents, but these two other agents are not visible to other agents in the group chat. So they are separate from the group chat. Instead, they are managed by the order management agent as sub-agents. So this is an example of the nested chat pattern I mentioned earlier. That nested chat between the order summarizer and the order retrieval agent are hidden inside the order management agent. But after their conversation finish, they will return back to the order management, and the order management will send the result back to other agents in the group chat. So you can see that how we can combine the different patterns and make a hierarchical conversations so that we can easily manage all the different levels of information. And also provide tools to only certain agents so that they don't confuse other agents. Cool. So yeah, hope that gives a overall idea about how we can define the most simplest agent using language model and then combine these agents of different types and build stronger and stronger agent. But eventually, you can still serve that complex AI system as a single agent that have a most natural interface and interactions. And to kind of briefly give an overview about how this product evolves, there are many kind of rich features I haven't discussed, but the most essential concepts I have introduced, that's the conversable agent and the conversation programming. Those patterns have been proved along the way that they can support many diverse requirements and accommodate with all the new technologies. So we initially started building AutoGen inside another open source project called Flammo. That's for automating machine learning and hyperparameter tuning. And in October 2023, we moved out to a standalone repo on GitHub, and that's the time it got a lot of adoptions. And we have grown a very large community with more than 20,000 members on Discord. And also along the way, we see that people are building all sorts of different applications from enterprise companies to startups to research. And they actually achieved very strong performance on the different benchmarks using their specific designs on building on top of the framework and achieve top performance, for example, on computer use in this OS World benchmark recently, on Sweetbench benchmark for software engineering tasks, web tasks like Web Voyager and Gaia benchmarks, and so on. Each of the agent it's not in a different architecture, but they all leverage the basic building blocks using AG2. So this just shows like just using the common building blocks, you can do many different kind of things and achieve very advanced and sophisticated use cases with them. I will explain. I will share some examples next. As I mentioned earlier, now we are building this AG2 in the community-driven open source effort. So all the open source founders and community maintainers have moved to this AG2 repo. And here, this slide shows some examples of the production use cases. You can find a QR code on the right to find the link and in the website that talks about some of the examples. I will just explain some of them. It's a very small selection of examples, but they cover many different domains. Some of them are more like a horizontal as an agent platform that supports diverse applications. For example, on Google Cloud, there's a agent engine product that supports AG2 as one of the open source frameworks, so you can deploy that on Google Cloud. There are all the other vertical domains focusing on some specific AI agents. That's quite interesting. I heard someone was building trading agents. Yes, we have seen multiple trading agent example, and there's also other applications like business automation. CGD is actually a European company working on that for handling like invoices, etc. Chip design, that's a very interesting use case. It's like made by NVIDIA very early. I'll share more examples from them. Customer support, cybersecurity, data engineering, and even areas like digital farming that's really far away from tech have been benefiting from it. And not only trading, and also there's investment research and marketing, and healthcare recommendation, marketing, software engineering, and task management. Yeah, so a lot of diverse examples, and quite a few of them are like advanced use cases enabled to explore the frontier of agentic AI. I'll mention a few examples. The first one I want to introduce is from NVIDIA. They are using it for some very difficult chip design tasks. And they have done this for multiple concrete tasks that usually take human chip designers days or weeks, but then they can use agent to save that time, reduce that time to minutes. In one more example, for example, the design rule checking code agent, code generation, when they just simply use the language model, they can achieve accuracy ranging from 40 to 70%. But after switching to this multi-agent design, they were able to achieve 100% accuracy and only need 2 or 3 iterations. That's a big game changer, so that they have been using that in production. And they have also achieved very impressive results for difficult Verilog coding and debugging tasks. And the learnings from that particular application is that even though these are several different subtasks in that domain, they find there are some common patterns. For example, they can use this hierarchical planning pattern to leverage the human expertise in a nice way, and that's the big, most important reason to change the performance dramatically. And in general, we see this is the case in many other successful applications as well. If you have the domain expertise and you know the right way to decompose the problem and leverage some playbooks from human experts, then usually you can do much better than simply relying on the internal knowledge of the language model in these agentic applications. The second example I'll mention is from Walmart. They have been using AG2 for some content generation and some marketing use cases, and they shared their lessons in the Google Cloud event earlier this year. And their key findings is that they use a planning agent as a group chat manager. The group chat manager basically is a special agent that manages the group chat and decides who to speak next if no user provided handoff conditions. So that's agent is very crucial, because after you define the roles of different agents, whether they can play together very nicely, mainly depends on whether you can choose the right agent at different situations. If you choose the wrong agent to speak, then it will slow down the process or even make the whole process fail. And they found one interesting agent selection policy in their application is to decide which one to speak next based on which agent is most likely to disagree with each other and sequence the debate, because they're using the multiple agents basically to do the debate about whether the current content has satisfied their specific guidelines, because they have very complex guidelines and the content must satisfy all of them. If you miss any single point of them, the result is not usable. So that's interesting discovery by them. And the next two examples, I will dive slightly deeper. One of them is for investment analysis made by Better Future Labs, and these slides are also provided by them. So the bottleneck in their this venture studio kind of business model is that they need to quickly evaluate a lot of business ideas and decide which one to invest and kind of find people to work on. So typically that takes a large amount of like human resources to kind of to do this work. They need to spend at least a week to do deep analysis about one idea and generate a report. And they want to basically reduce that time, for example, from 1 week analysis into under 1 hour without losing the quality. And they have built a system called Chandler, that's AI-powered due diligence. And they successfully reduced that multiple week of human diligence time to just under 30 minutes. And they have been using that, using AG2 since December 2023 and used in production and making a lot of iterations along the way. The successful solution they found is they define a hierarchical structure of the team of AI agents. This simulates a company that's there's one high-level director, and each director can manage multiple managers, and each manager manages multiple researchers. And since they follow hierarchy, they have very different roles. The director manages the high-level overall goals, and manager takes responsibility for one particular dimension of the objective. Again, this to make the generated report good to use, there are multiple criteria and multiple objectives, and you have to satisfy all of them. And they're using this hierarchical way to make sure every dimension meets the bar of quality. And each manager can manage some multiple researchers to do the work, but the manager will often push back to the researchers to say the quality is not good enough, you need to make more improvement. And so they can back and forth iterate until they meet the quality bar. And they found that it's quite crucial about how to design the consensus, how to make sure agents to reach a good consensus, because eventually they want to generate one single report that meets all the requirements. They found multiple important techniques to meet that. For example, we need to define very clear consensus criteria to specify what exactly constitutes this consensus. And they also need to make sure all the agents are aware of these criteria during the process. It's also important to clarify responsibility to make sure each of them is responsible for a very clear area. Finally, they also have some low-level kind of implementation tricks, like having right termination messages, using max turns as a fallback to prevent them falling into an endless loop, and some automatic failover mechanisms. Eventually, they're able to generate a very long report like this with a comprehensive structure of the report and nice charts inside it. So that's an example of a successful production use case and save a lot of human time. And another example is from also from Europe. This is slides are provided by Boris Bollet from Cambridge. They have been using AI agents to automate their research workflows. They started as a particular. Started from a particular domain of cosmology. They're doing a lot of data analysis using cosmology data, and also it takes a large amount of human time to do the analysis. Again, they are using AI agents to reduce that full day of work to just tens of seconds, entirely automated by agents, and the agent will produce equal quality result as human cosmologists. The type of workflows are like this. They have an interesting design called planning and control that separates the procedure into two parts. The first part is the planning phase, and the second part is the execution, or they call it control phase. In the planning phase, there are two agents, planner and planner reviewers. And planner will propose plans, and the reviewer will suggest improvements of the plan. And once they finalize the plan, they will pass that to the control phase. And in the control phase, there are more agents like engineers, researchers, software literature agents, and executors. Each of them will be equipped with different tools. And to make sure these agents follow the plans made by the first phase, it's very non-trivial, because if you simply provide a plan to the language model agent, you can't guarantee that that agent will follow every single step very nicely. They found you need to use a combination of multiple techniques to make sure they follow the plan. For example, you need to use a structure output, and then often you need to pass a subset of instructions. Like if you want the agent to execute only one step of the plan, you can provide only that step of the information, and also dynamically change their system instruction based on like which steps they have finished and which steps they still need to execute. And eventually they build a system like this. This is the interface of CMB agent. They can provide, and so after they make it working for the cosmology, actually they generalize into data analytics for any domains, so they can provide any data set of your specific domain of study and ask the agent to solve that task for you. Here we see that you can do some customization about what model to use, and then this is an example of like the planning phase. During the planning phase, we see that two different agents you can use the different models to do plans and plan reviews. After a few iterations, they reach consensus about the plan, so the planning phase is done, and they start the control phase. And during control phase, we see the different steps. All the steps in the plan will be executed step by step, and for each single step, the agent will the system will change the instruction dynamically. So they use some functionalities provided by AG2 called dynamic system update and structure output to make sure all the intermediate results are stored in the nice structure and nicely passed to other agents, and also make sure the agent only looks at the current step and not be confused by other steps. After and also you can see that some of the agent actually is able to execute code. They're given instructions about using some specific software. So this is all useful because for different domains, you might already have some domain-specific software that can help you analyze the data in that domain. And the agents, when you give the tools to the different agents, some of the agents will be use the general Python tool, and other agents can use this domain-specific tools. By combining them, they can get the jobs done. We see that the agents have been generating a very nice result using the using tools provided and generate a lot of different insights. And they didn't stop there. They actually take it one step further to work on a bigger project called Ignario, and that is a project for doing modular automation of scientific research with multi-agent systems. You can see there are many more scientists participating from many different domains, and the lead authors of this work, some of them from Pablo from Barcelona, Francisco from Flatiron Institute, and Boris from Cambridge. They are working in different science domains. Some are astronologists, some are like neuroscientists, some are biology, I think chemistry, even philosophy. And they have generated like hundreds of papers written using this software. Recently, it's also open source. Recently, you can check it out and find how they have evolved from a simple like cosmology agent all the way to this general purpose science agent that help you kind of automate many of the tasks. You can either do end-to-end automation using the system, or just automate certain steps in the research. For example, idea generation, methodology, analysis, and writing, paper writing. It uses many different frameworks to achieve that goal. So these are just a few examples I want to share, and there are many more. But some of them you can find from our community talks. If you we invite researchers, engineers, entrepreneurs of diverse backgrounds to share either use cases or some cutting-edge research or progress made by the industry and related. And we have been collaborating with all these different partners for building the ecosystem. Feel free to check our Discord channel and find the past talk information. And if you are a beginner, you want to learn how to build agent from scratch. There's a repo on GitHub called Build with AG2, and there let me quickly show you what it looks like. Yeah, so there you can find many examples of open source projects, so that you can learn from them. And there's also tutorials that guide you step by step from introduction to setup to understanding the core concepts and also some advanced use cases. So you can learn from that repo and also find some of the advanced use cases I mentioned earlier. Yeah, so that's the kind of the first part of the lecture I want to share about the AG2 open source agent OS. You can find the GitHub repo and also the Discord community. I would take a stop here to answer questions before we move on to the next part of the lecture. Yeah. Yeah. Yeah.
I think it's broken by time or something, so it just expired. So
okay.
If you can upload the slides so we can access the
okay. Links. Sounds good. So do you mean this QR code or the others?
I checked this one. I checked this one and the first one, I think.
Okay, cool. Yeah, we have a URL here, so yeah, we can find it later.
And maybe you already have another question, so
okay, please.
Maybe you will go out about it in the second part of the lecture, but this is a question that I had in mind like in the last few days.
Yeah.
But what is the balance between the model size and power to the number of inference calls that you want to do? So assuming we are not NVIDIA that can do everything she wants, but everything it wants, but assuming we have to choose some kind of balance, what are like the main points that we should consider when we want more inference or a bigger model?
Okay, got it. Yeah, that's a very interesting question. So if you think about this, the multi-agent system opens up the big design space that you have much more freedom than using a single language model. Because when you just use a single language model, often you need to use the most powerful one because you need to handle all the different situations with that one model. And as long as you have one difficult instance, and even though many tasks are simple, you still need to use the most expensive one. But when you start using the multi-agent design, the type of choices suddenly becomes much larger because you can decompose the task into many smaller pieces, and for each smaller piece, you can choose the right model for it. If that task is very simple, you just use the simplest model. If that is more complex, you use slightly more complex more complex model, and so on. And the overall latency or cost is not necessarily bigger than using a single language model. Yeah, so this is like one interesting reason to actually use multi-agent systems to not only have better quality, but sometimes also reduce the cost and reduce latency. Another question? Yeah.
Hi, thank you for this first part of the talk. I'm curious about how you see non-LLM parts of an agentic system, a multi-agent system. Mm-hmm. Is there a place for it? And with that in mind, how do you keep in mind the black box nature and the lack of verifiability of LLM tools? Is there ways to, there's a lot of papers that can be made very quickly, but how do you evaluate the value of this? Or are you doing it afterwards or as part of this? Is there something that's not LLM based to check it?
Yeah. It's a great question. So non-language model has a big place. It's not only there's a place for them, there's actually a big place for them. So pretty much all the applications I've seen, all the successful applications have at least some non-LLM elements there. If you think about it, they're everywhere. So on the agent backend side, some of the agents in the AG2 system are like backed by non-language model tools like code execution or any like browsing tools or computer use tools. Yeah, you can use all these advanced tools as backends, not necessarily using language model. And there are in the conversation programming part, often you need to use rules or programming language to precisely define the conditions about transitions from language model to language model. From agent to agent. And even though language model can be still used to handle some of the ambiguities, they're not always reliable. And using the structured information, structured context variables has been very important in multiple of the use cases I mentioned. And there's also the like verification part, as you mentioned, including like security verification, success verification, and so on. Recently, we had a talk called MARIS, a security control development paradigm for multi-agent collaboration systems in the bottom there. And this done by a security team from University of Illinois at the Brandon-Champaign. And they have find some ways to insert security checks at all the different places of language model connections with other language models or with tools. So all the connection points, you can insert those checks. And they actually won a recent competition called Agentic competition from Berkeley Agentic AI Summit. And we are making integration right now into AG2. Actually, they already finished integration, but we're like merging that to the AG2 repo so that all the users can also benefit from that. Yeah, these are just some example, but there's a lot more. They're basically everywhere. Yeah.
Thank you.
Okay.
Thank you for talking. I have a question. Like in a multi-agent system, like all agents should be from the same model or can be from different language models. For example, model 1 from ChatGPT, model 1 from Gemini.
Yeah.
Gemini, sorry.
Absolutely. Actually, in my next part, I will talk even more about that part. So we have a very new recent exploration that make that. Using diverse models and agents as one of the central design considerations. That's all for the question, and then I will share that soon.
Okay, thank you.
Okay, thank you. Okay, probably let's move on. Just quick recap. Oh, yeah, the one more question.
So the question is regarding the development of the agents, given the huge design space and complex problems that are being solved. So what are the current best practices? Because ideally you would have test set but here, for example, in scientific research, it's hard to make. And so how is it done? Do people really create some kind of test sets, or do they just play a bit with a new iteration of the system just to see that it works better? Or yeah.
Got it. Yeah. So I think the humans still need to do a lot of inspections right now. And one good thing for a G2 type of system is you can switch the backend of agents from language model to human at any time. So maybe, for example, in the beginning, you can make the human input mode as always, so that before agent responds to other agents, they always ask for your input. So you always check the current message sent by other agents and think about what's the right reply. But once you are confident that one agent is doing the right job, you can switch the mode to automatic and focus on debugging other agents. So actually, the multi-agent design makes that unit testing for each single agent simpler because you can separate the concerns and just focus on testing one particular functionality of an agent. Yeah. So in general, I think this is this is one of the best practice suggestions. Another suggestion is when you start with putting all the instructions to one language model agent and give all the tools to solve your task. But you still need to check the output, check the logs, and if the if it doesn't solve the task, if it doesn't solve the entire complex task, you may want to think about decomposition. We actually have a few other tools to help you do the evaluation. We have an agent-based evaluation solution called Agent Eval, so that agent can automatically check your log and provide analysis. Sometimes they can even break down the overall success metrics into sub-dimensions and give you evaluation on each of them. So not only you can build your solutions using agents, but you can build your testing. You can make the testing part also automated partially by the agents. But again, you need to verify whether the testing agent is doing the right thing. So humans' role is not completely removed in all these different situations. Any question? Okay, so let's move on. So before I talk about the next open source project called Mastian, I want to briefly recap that we want to eventually North Star to build AI agents with natural interface, strong capability, and scalable architecture. Some of the most, so I want to talk a little bit about the progress in each dimension. For example, for the interface part, today's AI agents have been gaining size and sounds. For example, Gemini Live, it can use your camera on your phone to see everything in the world and speak to you in real time. Some of the early prototypes I've seen also can see your screen and provide real time like actions and trigger actions on your side. So these provide some promise of very kind of a good understanding of everything around you, and make sure that they can kind of solve tasks in real time. And so that's in the interaction side. On the interaction side, but there are still challenges, and we need to, for example, make sure the context can flow across devices and let the agents know like when to engage versus when to stand back. Yeah. And on the capability side, we've seen that coding agents like Cloud Code, Gemini CLI, etc., they have been integrated into the developer workflows. They can write and refactor code autonomously. And things like ChatGPT agent also integrates browsing, write code generation, document generation into a single workflow. So these, and it's a big deal because the coding is a meta power. So if an agent can self-modify its own code, own software, then it can also self-improve because they can experiment, modify, and evolve, or even spawn some agents. But to realize that North Star, we need to solve tasks, hard problems like long-term memory, cross-session reflection, and make the agent able to learn by interaction. And the future breakthroughs will come from collaborations of diverse minds. So we have seen that all these different backends, different models have been working on stronger and stronger agents. Like you just asked, can we amplify their power by scaling them up, right? Making them working together as one. AG2 has been focusing on that, and there's a new project called Mastian that's pushing that further, and by orchestrating all of them together and working in parallel and checking each other's results and share intelligence. So the hope is that we can achieve exponential growth. Whenever you have a stronger single agent, you simply add that to the system and then amplify the power of the entire system. There's also a big challenge we need to solve in consensus, in shared context, and in interoperability. But it's both. In future, we can weave all these layers together, like the sensory richness, the self-evolving and coding capabilities and the scalable architecture, then potentially we can achieve the North Star and build AI that grows with us. So just to recap that's the big vision. And with these all the open source projects where we are building them together. So that's the kind of this part of slides, and I actually want to talk about this messaging because it's a very new open source project. I want to share some very recent progress of that, and also answer the question about integrating with multiple models and AI agents. So I'm going to switch slide for that particular presentation. Okay, so I have about 10 minutes left. Okay, so this let me make it a bit larger. Yeah, so as I mentioned, messaging is a very young project. It's roughly kind of 1 month, a little bit older than 1 month, and so it's still fast growing. And the motivation we have pretty much covered that. The single AI model or agent often has limitations. I don't know how many of you kind of are using multiple AI agents together. Maybe you're already doing that, and probably many others. Could you raise your hand if you're using multiple AI products or AI agents at the same time? Yeah. Could you share like one reason of doing that?
Sorry, I'm not familiar with LLM, but previously when doing deep learning projects, sometimes we need to get modalities from video, sometimes get modalities from text, and the different models they have different capability for different modality, and then we did a combination, so that is why.
Okay, good. Any different reason than the input modality? Yeah.
Mainly cost. I would say that, especially when you start using, I don't know, React, and you want to have different models, you want to cut costs as much as possible. So at one point, what you try to do is maybe a big model for planning, but then basic tasks, the simplest model, the cheapest model as possible. So that's the main rationale behind it.
Good. Great. Yeah. So cost is the input modality, cost. Any other reason? Okay. So yeah. So I think there are some examples of reasons indeed. And if we think about even from the capability perspective, the different models, providers, and agents, they have evolved a lot. Like compared to, for example, 2 years ago, when we only had GPT-4. The progress has been a lot. So right now, for example, most of the major AI products have integrated the tools like search, code execution, and others. Some even have computer use, etc. So we have seen that the single agents capability have been evolving. But there's still room for there are still limitations. Because for really complex tasks, even the strongest single agent still are quite limited, and they often only have a single perspective, and they have limited context, no peer review or validation, and often they do sequential processing. So we want to go from isolation to collaboration. And explore the frontiers of that multi-agent collaboration. Even so, after all these single agents and single models have evolved, and what's the best way to leverage them to still perform nice collaboration, solve even more complex tasks. There are many potential different ways. As I mentioned, in AG2 there are already many different patterns. But in messaging, we are trying to explore a even newer and newer frontier of a study group type of parallel task solving and having shared intelligence. So I asked the single agent, all the single agent, to try to solve the task, but from different perspectives, and aggregate the answers, make iterative refinement, and eventually achieve this multi-agent scaling effect. Because we basically want to test the hypothesis whether there's a simple way to scale up the power of multiple agents by simply adding new agent systems without making a lot of customized design choices. This is quite different from the AG2 approach. As opposed to the customized design for each particular application. We want to see whether there exists some universal way, just like how we define deep neural networks. And we define the basic components, the layers, the neurons, and then we simply scale them up. We simply add more neurons, more layers, and the power of that nicely scale up. But we see that scaling has shown a sign. There's a sign that type of scaling hits a bottleneck, right? For example, the GPT-5 is delayed a lot from the initial expectation when after people see the GPT-4, and the intelligence seems to be not as high as people expected. So we're exploring a new dimension of scaling, as whether we can scale up intelligence without changing the model, right? We just simply use the best models we have, but by adding the inference power by using the agents and tools, is it possible to achieve a similar scaling effect? Like we just simply add more agents, more diverse agents, and the system suddenly becomes more and more stronger. So that's kind of the hypothesis we're testing. We don't know whether it's whether we can achieve that, but there's already even early signs of encouraging results. And if you want to look at the root idea, the initial idea, you can check that blog post I wrote earlier in this year called "Myth of Reasoning." So there's a link, root.messaging.ai, that links to that article. But basically, this project built on the previous multi-agent research we have been doing from AG2 community and evolved from that community-driven innovation. And one example of this multi-agent collaboration is from the recent release of Grok Heavy and Gemini DeepThink. They all use the same model. They didn't change the model, but they use some clever multi-agent design to have a big improvement in the performance, and then they price much higher compared to using a single agent. So that's a strong kind of commercial evidence that multi-agent scaling is potentially a viable idea. And here's a systematic architecture of messaging. We basically have orchestrator that takes a human that take a user's input of a task and then distribute that task to all the different agents. So here in this diagram, you see clearly there are different backends. You can have Claude Code, Gemini, GPT, Grok. You can configure all the different backends, including some local models and cheap models. Whatever models you like to use, you can configure them as different agents. Or even using the same model, you can create multiple agents of different instructions or different conversions and different tools. So it's very easy to create these diverse agents in the ways you want. And the magic happens when the multiple agents try to first solve the task independently, but then share their progress and learn from each other. So there's a shared collaboration hub that enables that. The key features include this cross-model synergy, so that we want to leverage the best strengths from each single model or agent, and make them try to solve the task in parallel, but make the iterative refinement along the way, and eventually reach nice consensus. I will fast forward. I will briefly mention the technical design. We use async streaming and dynamic scheduling so that all the progress are streamed in real time from agent to other agents. we unify the different backends by trying to leverage both the common functionality from different agents as well as the unique strengths of each agent. That's a challenge because the different agents often have different interfaces, different APIs, or some of them have unique capabilities. But we want to still make them able to do their best work and in the same time able to evaluate others' work. So there's some big challenge about how to unify and how to make them work in a unified way, but not losing their unique capabilities. But our basic design is to have a binary decision framework. So we ask each agent to either make a choice of existing answers and vote for existing answer, or generate a new answer. So the agent must decide whether there's already a good answer currently, or there's no good answer, and they need to generate a new answer by considering all the existing answers. And as soon as one agent generates an answer, the voting will restart, and all the other agents will look at the result and vote again until no new answer is generated and all the voting is finished. There's some big context sharing challenge, for example, for the coding type of agents, because each agent has their own workspace and they generate a lot of files. And how do we allow the different agents to understand the work of each other and properly assess them? And we can't use this. We can't just simply allow them to work in the same workspace because that will cause conflicts as agents are working in parallel. And we also cannot completely isolate their workspace because there's no way for them to understand others' work then. So we figure out some current solutions that solve that problem, but there's still a lot more to research in that space. But basically, we allow the agent to have a permanent workspace and temporary workspace that stores the copies of other agents' work, and allow them to check the answers and even execute code temporarily. But eventually, they need to generate their own answers in their permanent workspace. In this way, we can have agents of different roles. They all can write code and read others' code, and eventually collaborate together and generate combined solutions. There are some preliminary results showing that several different benchmarks using this approach, Nestring can match or surpass the best single agent on each benchmark. By the way, the winner on each benchmark is different if you only use a single agent. This also confirms what I said earlier, that the strengths of different agents are different. And there, if you look at the oracle for the GPQA, meaning that if we can have oracle that choose the best agent for each single instance, it's possible to achieve 95% on that GPQA task, and just by choosing the best single answer from the best agent. But currently we're not there yet. We're only at 87%. That means there's still large room for improvement for this collaboration. And actually, we should be able to even go higher than that because we allow the iterative refinement. So the agents don't simply generate answers just once. They actually can iteratively generate new answers. So there's a lot of exciting research ahead. And there are both successful examples, like initially none of the agents generate the correct answer, but after checking the answers, some agent is able to find out the problem and generate a new answer. So this is what I meant by why it's possible to even go beyond the oracle's performance. But there are also other cases where some of the agents generate the initial answer correct, but after the voting, the agent picked the wrong answer, and mainly because the wrong answer contains more comprehensive analysis and reasoning, but that misleads the other agents. So there are a lot other kind of research we can study, like for example, what happens if we make the voting identified instead of anonymous, and what happens if we include the currently voting results. So we see some interesting behaviors like self-voting and herding behavior when we change these designs. So these are just some simple examples of what we can explore with the current research. and we have some early momentum with early adoptions and good growth of community. And you can find some interesting case studies from case.mastering.ai. This is also part of the GitHub repo. And some of them are very advanced, using like combining multiple coding agents, for example, to build websites or to working your own file system and generate like slides for a topic. And in general, the scaling multi-agent scaling opportunities happens when the diversity of thought can help. For example, for complex analysis tasks, for creative tasks, or for coordination that requires agents using their different tools and different perspectives. You can go to the GitHub repo and quickly get started using Python and CLI. We support all these different major models and agents, and allows advanced tools. As I shared earlier, the vision is to achieve the to explore whether we can use this multi-agent scaling to potentially achieve exponential intelligence. And there are a lot of big challenges we need to solve, like the context sharing, the memory, and interoperability. So if you're interested, also check this new Mastering project alongside with AG2, and see if that if you can leverage either AG2's mature framework for your production use case, or explore the cutting edge frontier of multi-agent scaling using Mastering. I think I'm out of time. Thank you very much.